Good evening, everyone. So as Louis said, I'm Laurent. I'm a co-founder and CTO at Radix, who I'm representing here this evening. And I'd like to share with you a bit about the magic of large language models with you this evening. So let's dive right in. First, I'd like to briefly introduce Radix. Then I'll give you a definition of large language models, since that's really the topic of this evening. I'll show you a bit of the magic of large language models with a quick demo that I think is kind of amazing to see. And then I'll follow that up by trying to dispel some of that magic by showing you a little bit about how large language models work under the hood, as well as telling you a little bit about the limitations of those models. Next, I'll describe a few types of applications that you can build with large language models, new experiences that you can make possible with large language models, and also give you a framework that you can use to design or come up with your own ideas for applications of large language models. And finally, I'll end with an outlook on what the future may hold for large language models and AI. If you have any questions during the presentation, don't hesitate to just raise your hand and ask. That's absolutely fine. So first, who is Radix? So Radix is an AI partner. We're an AI partner for our clients on their AI journey, going from their 0th to their first AI solution, from their first to their second, and so on. That is a journey that they're on, and we're there to guide them. What do we do on this journey? We help them with tailor-made AI solutions, with tailor-made AI services along that journey, which we optimize for impact, both for the business as well as for the end users. And we do that across different industries and across different AI domains. We were founded in 2018. We have offices in Brussels and Ghent, and now have a little over 50 colleagues. These are some of the clients that we're working with, so you can see across many different industries, which we find really interesting because we get to cross-pollinate ideas from one industry to another. You see industries like life sciences, manufacturing, healthcare, public services, and so on. And we're also active across different AI domains like natural language processing, which is the topic for this evening, but also tabular data, computer vision, planning and scheduling, are some of the bigger ones that we're active in. All right, so what are large language models? Well, I'll begin by defining what an LLM, it's abbreviated LLM, is exactly. Really, you can think of it as a function that you give it a piece of text. In this case, I'm giving it the text. The best thing about AI is its ability to. And then the only thing that the large language model does, the only job that it has, is to predict the next word in that sequence. So what could be a next word for that input piece of text? And it gives you multiple options, and it tells you the probability of those words being the correct next word in that sequence. That's the only thing that a large language model does, is to predict the next word along with the probability. So clearly, if you give it a piece of text, you can pick one of these. That's called sampling. You can sample one of these next words and use that to append to the input text. And if you do that successively, so we pick one of the words, not necessarily the one with the highest probability, but maybe we can pick it according to the probabilities. We pick a word, we add it back to the inputs, and then we ask again to the large language model, now what would be the next best word to complete this sentence? If we continue to do that successively, we can see that we're starting to generate text. So that's really the core of a large language model, is to generate text by generating words one by one. So if I take now a large language model, and I've trained this large language model on basically the entire internet, many different corpuses of text go into the training of such a large language model. It is trained by asking it to predict the next word in a piece of text, and then comparing it with the actual next word in that piece of text. So that's also how it's trained. So if I take that large language model and I give it an input sentence, in this case, I'm giving it a small riddle. I'm asking, Alice has 3 brothers. Each brother has 2 sisters. How many sisters does Alice have? So if you think about it a little bit, clearly Alice is one of those 2 sisters, and therefore she only has one other sister. However, the response from the large language model is not Alice has only one other sister. The response is something like a multiple choice set of answers, which is a really strange kind of completion at first sight. But really that's to be expected, because in the context of this sentence, the most likely way for the large language model to complete that sentence is not with an answer. It thinks, oh, this must be part of some kind of like math or textbook or a high school textbook, and I'm supposed to give the user multiple choices. That's more likely than actually giving an answer to the question. And that's because in the training set, it's this type of question multiple choice answer is more likely than actually having questions and answers. So the base large language model, all it does is complete documents. Now, what changed at the end of last year around November is that OpenAI have taken that base large language model and have continued training it with something called instruction tuning. And instruction tuning basically asks this large language model, hey, now I want you not just to give me the most likely next words, but we're going to change slightly the probabilities so that the format of the answer looks like an actual answer to the question that I'm asking. So that's the instruction-tuned version of the LLM. And this, what you're seeing here is a screenshot from the OpenAI Playground, where you can interact with both the base large language model as well as the instruction-tuned version to really see kind of these differences. So this is really interesting, because now if I ask the same question, I get an actual answer. The answer is incorrect, but the format of the answer is what I would expect. It is answering my question. And what's also interesting is that I can inspect the token probabilities. So basically the probabilities of the words being generated, which we know is one of the outputs of a large language model. So I can hover over the number 5, and I can see that the probability of that being the number, that being the word that it wanted to insert there, was 11%, which it's completely wrong. And actually, its confidence in the number 4 being the right answer was the highest of these alternatives. It actually thinks that maybe Alice has 4 sisters, which is also completely incorrect. But nevertheless, this is an interesting thing that we can kind of observe from this large language model. So now we know what large language models are. When we talk about large language models, usually we're talking about the instruction-tuned version, no longer the base or the pre-trained large language model. We're talking about the instruction-tuned version. And what is then ChatGPT? ChatGPT is a web application that is built on top of an instruction-tuned large language model called GPT-4, which is the latest version of OpenAI's large language models. So if I go to this web application, ChatGPT, and I ask ChatGPT, I give it the same riddle, unfortunately, its answer is also incorrect. I lose the ability to inspect the probabilities of the token, so I cannot see what it thinks the alternatives might have been. It is incorrect. It used to be actually, the reason it's incorrect is apparently there was some regressions with GPT-4, performance regressions, because in the first half, I want to say first half of 2023, it did actually get the answer correct. And it seems to have regressed since then. People have also, you might have heard about that, complained about it being more lazy, not wanting to fully answer questions. So I'm sure OpenAI is working to deal with those issues. All right, so that's large language models and ChatGPT. So now I'd like to show you a quick demo for those of you who haven't really fully experienced ChatGPT and its possibilities, to kind of show you how magical they can really be. I'll switch to a different tab. I hope that's visible. So I dragged and dropped a CSV file into my chat window. And the CSV file contains basically the top 10 most popular stocks in the US and their price history. So basically the price at every date of the last couple of years. Here are some historical prices of different US stocks. Can you plot them on a risk return graph for me? Use annualized risk and return. Unusual activity from my system. Oh, okay, it does start doing it. So the first thing it's doing is it's using the large language model to write code. So word by word, it's generating code, and it's running that code to see what's inside of the CSV file. You can see the contents of the CSV file here. It's running that code to see what's inside of this CSV file, to understand the contents. Next, it's writing code to create that graph that I asked. I asked it to create a graph to show me the risk and the return of these different financial instruments. So if this runs correctly, it should show me a graph. Yep. So if I scroll up, this is the outputs of running the code that it generated word by word as a response to my question, which I think is kind of amazing. All I did was upload a CSV file. I asked it to create a graph. It generated code. It ran the code. And it shows me the results of running that code. And it shows me that different companies have a different amount of risk and a different amount of return. Now I can continue working with this, and I can ask, can you create a minimum volatility portfolio for me? Yeah, let's just try that. So minimum volatility means I want it to be to have minimal risk, essentially. Let's see what it does. So it's writing codes that will optimize. It's using SciPy. SciPy is basically the scientific computing library for Python. And it's using the minimize function. So it's going to optimize some kind of objective function. It decides that it's going to optimize the volatility. Let's see what I get back. And it creates a minimum volatility portfolio for me. All right. So I'm not super happy with the result. Why not? Because J&J represents 55% of this portfolio. So I'll ask, can please limit the positions to max 25%, and I'd like a return of at least 12%. So
what it did with J&J was right, based on what you're in.
It was, well, I haven't checked, but if I were to check, I'm assuming it's going to be correct. So now it's taking into account my comments. It's not exactly what I wanted. So it recomputed the results, taking into account that I want 12% return, and I don't want the positions to be more than 25% each. It's a bit slow. And it summarizes. So this is the output of running the code, which is more of a technical, it's a JSON output. But it also summarizes that results in natural language for me, which is a bit easier for me as a human to parse. Just give it a second to finish writing. Yep. And now I'll end with one final step. Now can you add this portfolio to the graph you created earlier? Because I'd like to compare this optimized portfolio with all of the individual instruments and see how that compares. Yep, sounds about right. So I did ask for a 12% return, and you can see that it's hovering around the 12% return line, which is good. Its volatility is also way lower than most of the instruments that I provided. So that looks like a much more interesting option for me to invest in than investing in any random combination of these stocks. So that was a very brief interaction. I did begin by uploading a CSV file. You can actually ask it to generate codes that will produce that CSV file. So even if you don't have this data, you can just ask, I would like the price time series of the top 10 US stocks. Can you generate a script for me? And it'll do that as well. All right. Yep.
Questions,
sure, yeah, it's fine to ask questions.
What plugins did you set up in ChatGPT in order to do
that? I haven't actually enabled any plugins manually. I believe that so what this is using is the code interpreter. which is, I believe, now built into that. That used to be a feature that you had to enable manually, but I believe it's now built into the ChatGPT Plus version of ChatGPT. So you don't need to manually enable it. It will just detect, oh, actually what the user is asking is something that should be responded to by writing and executing code. And that's what the code interpreter does. It decides I should write code and execute the code to answer the user's question. Not all questions require writing and executing code, but these questions that I just asked, they are better responded to by writing and executing code.
So ChatGPT figured that out by itself. It's on you that
I did not have to ask. No, indeed. It automatically detects when would be a good time to write and execute code, as opposed to just answering with natural language. You can steer that to some extent. It is possible to customize your ChatGPT experience by saying, I prefer you to write code when it is possible, and then it will increase the likelihood of it generating code. Or you can say, I don't want you to ever write code because I'm not a programmer, or I don't want you to do that. That's also possible. And then you will decrease the likelihood of it writing code. Yeah. So I think you'll agree that that was kind of magical. Yeah, there's another question.
How do you know that this question it needs to instruction or learn?
It could be both. I'm not sure, to be honest, how exactly they achieve it, because initially when ChatGPT was launched, some of its behavior was instructed by really explicitly using natural language to instruct it to not do certain things or to do specific things in response to the user's question. So it is certainly possible that they have some kind of hidden prompt that we don't see that says, when the user asks this type of technical question, you should begin by writing code. That is possible. However, I think it's not likely that that's what's going on right now, because over time, they actually reduced their reliancy on this so-called system prompts, which is kind of like the hidden prompts beneath ChatGPT that instructs the large language model how to respond. They've reduced their reliancy on that and have more embedded the way in which it responds directly into the model. So there is no hidden prompt, let's say, although that is still a possibility to control the outputs if you want. Yeah. Yes. Yeah. That's a good question. I'm not sure if it would be able to write in a different language. Python is definitely the best supported one, I believe.
I use it for C# all the time, and I'm astounded how good it is.
Yeah. Does it actually execute the code if you ask it to?
No, I've done stuff that has executed, but I can't remember in what
context.
Context.
It can certainly generate code in any language, but I'm not sure if the code interpreter will actually run the code if it's not Python. That is something I'd have to check. Yeah.
I'm sure it does in another language, because I don't work that much with. Sure.
Yeah. Yeah, it's certainly possible, and there isn't really a reason why it wouldn't be possible. So good. So that was kind of incredible. Certainly, it would have surprised me a couple of years ago that an experience like this would have been possible. Next, I'd like to dispel some of that magic by showing you. Yes, another question.
How do we feed the data to things?
Yeah.
Specific application.
Yeah. So there is really just one way to feed data to LLMs, and that is through the input text. That's not exactly so there are some more complicated techniques, but generally the main way is to feed the data through input text. So in this case, the contents of the CSV file would have been passed as part of the input prompts to the actual underlying LLM.
No, that's not my question. My question is,
okay.
when you have your, let's say, take ChatGPT as an example.
Yeah.
If we ask a question, it does respond. For every prompt, there is an equal response.
Yeah.
How does the ChatGPT learn by itself without feeding the data? That is, it's not calculating by itself, it's not throwing by itself, but it is being fed by.
I think that's what I'll cover a little bit with the dispelling the magic of LLMs in the next section. I'm not going to go into a lot of detail, but I just want to give you a sense of how it generates that text, because that's really the thing. When people see this, they think, how is that possible? How did it know how to understand my question, how to produce that code, how to execute it, and actually, give me the answers that I was looking for? So that's what I'm going to try to explain in the next section. So the first thing to know is that all large language models are transformers. What is a transformer? A transformer is basically this diagram that you see in the middle of the slide here. This was something that was developed mostly by Google researchers in 2017, and is an architecture. That means it's kind of like a structure, a way to organize computations going from input to output. So from the input sentence to the predicted probabilities of the next word. This architecture is now a couple of years old, still hasn't been dethroned. And pretty much every large language model, whether you're using ChatGPT's GPT-4 large language model, or you're using Mistral's, so a French startup, Mistral's models, or Meta's models, they're all really the same architecture. They're all the transformer. They're just different shapes and sizes, trained on different bits of data, fine-tuned on different data, but really it's the same model that we're all interacting with. So that's the first thing to know. So next thing is, okay, what does that transformer do exactly? So we've already seen this. The inputs to the transformer is a sentence. So for example, a cat has 9, and your internal transformers will automatically say lives. That's the most likely next word in that sentence. But also the transformer will do essentially the same. It will take the same sentence, process it through a series of steps, and outputs the probabilities for the next word appearing in that sentence. So lives would have a high probability in this case. So the next couple of slides are a little bit more mathematical. My goal is not to explain like the detailed mathematical operations, but I do want to give you a sense of how do we do this? How do we go from this text to these words, right? So the first step is, well, computers or machine learning models, they can't really work with text directly. That's not possible. So the sentence, a cat has 9, that isn't something you can feed to a machine learning model, not immediately. So first step is to turn that text back down to numbers, kind of like how an image, if you take a picture with your smartphone, those pixels are all really, they all have a numerical value, a red, a green, and a blue value. Well, in the same way, every word in this sentence will be associated with a number, an integer. So for example, the word a will correspond to the number 1. A space might be the number 0, has the number 23, or cat is the number 23, and so on. So that's the first step, is to go away from the text and to represent it as integers. And then we can take those integers and use them to look up rows in a so-called embedding matrix. So an embedding matrix is just really a big table with as many rows as there are words, and a fixed number of columns, 12,000 columns. So what I can do is I can go and say, okay, I'm going to look at the word A, which is the number 1. So I'm going to the row in the embedding matrix that corresponds to row number 1. And I'm going to take that out of the embedding matrix and I'm going to stick it here. So these are 12,000 numbers that represent the word A. I'm going to do the same for the space. I'm going to take out the 0th row of the embedding matrix and just paste them here. Same for cats, and so on. And so now I've taken what was originally a simple sentence and transformed that into this white box, which is really just a numerical representation of that sentence. This is important because the rest of the transformer architecture is really a series of operations on this matrix. Does that matrix make any sense initially when you start training a large language model? No, it doesn't. But the point is that a large language model will update the embedding matrix and every step and every operation that happens on those numbers according to the data that it sees during training. So the yellow box is essentially trainable. It's something that can be learned from the data. So while it initially doesn't make sense, over time, these numerical representations of these words will start making sense. You can see that, for example, because you can start doing arithmetic with words. So if you do, for example, if you take the word king, which has a numerical representation, you subtract the word man from that numerical representation, which also has a numerical representation, then you have a vector, and that vector, and then you add the vector for woman. So king minus man plus woman, that ends up with a vector that is very close to the vector for queen. So you can see that it learns some of the inherent structure in our language in that way. So as I mentioned, I'm going to gloss over these details, but this input matrix, this kind of numerical representation of the input sentence, is going to be transformed by a series of matrix multiplications with trainable matrices. These are matrices the model is allowed to learn. And then comes kind of the magical ingredients, which is called self-attention. This is kind of what makes transformers unique, perhaps what makes it work. And the principle of self-attention, without explaining the mathematics behind it, is that different words in the sentence can attend to different other words in the sentence. I'll give you an example. If I tell you I'm going to the bank, and the bank is beside the river, when I add that second bit of the sentence, it really changes your interpretation of the bank. Initially, when I said I'm going to the bank, you might have thought I was talking about a financial institution. But then when I said it's beside the river, maybe you updated your interpretation of bank to the river. He must be talking about the river bank, which is a completely different type of, concept. And that's really what's happening here, is that the meaning of one word can be influenced by the other words in the sentence. That's what the self-attention mechanism does. But it really is, again, just matrix multiplications, another set of matrix multiplications. So the matrix multiplications, the self-attention module, they're basically all stacked into a layer called multi-head attention. And then returning back to the original transformer architecture, we have this multi-head attention layer that I briefly described. We have another layer called a fully connected layer. I'm not going to explain it, but it's another matrix multiplication. And then really this thing here, the bulk of the transformer, is just stacked 100 times. So you do it once, but then you do it again, and you do it again, and you do it again, and you do it 100 times. And that ultimately ends up with a simple vector that says what the probability is of each word that could complete that sentence. So a cat has 9. Lives would have a probability of, let's say, 95%. Whiskers might be 4% or whatever, and so on. And then maybe castle would have like 0%. Oh, a cat has 9, castle doesn't really make any sense. So that's how we go from input text to probabilities for the next word. What can we learn from this? Well, we can see that to an extent, large language models are imitating some of our cognitive abilities. We have the cognitive ability to write text, to write code, and being able to predict the next word in a sequence is kind of an imitation of that cognitive ability. That's explicitly what we're trying to teach the large language model to do. We're not trying to teach it to learn what consciousness is, or to be sentient, or to have will. Those are not present in the goals that we have for the large language model. That's not something that we're training it to do. So those are things that we shouldn't expect it to have. It's going to mimic, it's going to learn what we're teaching it to do, which is to predict the next word, i.e. a subset of our cognitive abilities. So here's a mental model. How do we describe the cognitive abilities of humans? One way is with a so-called T-shape. So a person's T-shape kind of describes both the breadth and the depth of their abilities. The breadth of the T describes how much knowledge you have across different domains, the breadth of your knowledge across different domains, while the depth of the T kind of describes your ability within a given domain. And if you were to compare a human with a large language model using this analogy, you would see that a large language model is superhumanly wide. It knows way more about way more topics and skills and knowledge than a human could ever hope to do. Why? Because it has read the entirety of the internet. No human can ever read the entirety of the internet. It's estimated that it would take something like 20,000 years of non-stop reading from morning till evening to be able to read the entirety of the internet. So no human can do this. That's why it's superhumanly wide or broad. However, if you compare the depth of the T between a human and a large language model, you'll see that the depth of the large language model is subhumanly deep. A human is in a given domain far stronger in its abilities within that domain than a large language model is. Any of the jobs that you guys do, you'll be far better at those jobs than a large language model is. And you can kind of see how this makes sense. Why is this the case? You can kind of see it from the objective of wanting to predict the next word in a sequence. So I'll show you that with two examples. So the breadth of the T, let's take an example, a Wikipedia article on Elon Musk. And I've highlighted some bits of knowledge in that Wikipedia article. For example, I've highlighted Elon Musk's birth date. I've highlighted the name of his brother, his net worth. Those are all little bits of information. If I'm training a large language model to predict the next word and I blank out his birth date, and I wanted to predict the birth date correctly, it has to somehow learn the birth date of Elon Musk and store that in a compressed way inside of the model. So you can see how wanting to predict the next word accurately requires it to download and store all of this information inside the model. Otherwise, it wouldn't do a good job of predicting the next word. And similarly, if I give it a riddle like Sally has three brothers, each of the brothers has 2 sisters, how many sisters does Sally have? The next word in that sequence, the fact that you would want to say 1 sister, requires you to have understood the previous words in the sentence to really understand what the question is asking. You cannot answer the next word correctly without having solved the riddle. So that means that the depth of the T, that even though all it's doing is learning to predict the next word, it has to somehow develop some kind of reasoning ability. And we call that an emergent property. It's not something we explicitly wanted it to develop, but because we're asking it to predict the next word, it has to somehow learn how to reason, to be able to answer questions like this accurately with the next word. But you can see, because we're not asking for it explicitly, the depth of the T also won't be very, very deep. It's just a side effect. It's an emergent property. So we have all of these downsides. We have we know that LLMs are weak at reasoning, weak at planning, that they suffer from hallucination, because to the LLM, hallucination is really just when it's predicting the next word. If it's the most likely next word, yeah, then that's fine for the LLM. It doesn't matter if it's true or not. All that matters is that it seems plausible, that it's likely. So those are some of the downsides. So what are people doing, or AGI companies doing, is they're aiming to build AGI, artificial general intelligence, which is like a step up from large language models. And the goal of AGI is to reach median human depth in this T profile. So human experts can go all the way here, but the median human, so let's say the middle of the pack, reaches a certain depth. And the idea is, the goal is, we want to be able to reach median level with LLMs as well. And when we've done that, we've reached AGI. We can go a step beyond that. If we can reach the level of human experts within their given domains, then we can say that we've reached artificial superintelligence, ASI. I would say at the end of, during the course of 2023 and also at the end of 2022, some kind of recipe for success has started to emerge for training large language models that are useful to us as humans. This is a slide from Andre Karpathy's State of GPT presentation. I've tried to condense it down. There used to be 4 steps. We can now kind of summarize those as the 3 steps that are required to build a high quality large language model. And I'll kind of show you. We've already discussed, I think, the pre-training phase, where we try to complete documents. We've also discussed, I would say, the sum of these 2, but I'll try and disentangle these a little bit so you can kind of see how this recipe leads to such an amazing experience. So the first step in this recipe to train a successful large language model is, the training task is simply to predict the next word. And we do that across, let's say, the entirety of the internet. Each time taking a document like a web page, taking a piece of text out of that and asking it to predict the next word, and that for the whole internet. The outcome of that isn't particularly useful. We already saw that, and when I gave it the riddle, it gave me some kind of multiple choice answer. But there is a useful outcome. What is the useful outcome? It is that we now have kind of a compressed version of all of the world's knowledge. It's all inside of this large language model. It has to have learned this knowledge to be able to, for example, predict Elon Musk's birth date correctly as the next token. It has to compress that knowledge. It won't be perfect. That's why it's lossy. That's why it may hallucinate, but most of it should be in there. Next step is instruction tuning. So in instruction tuning, what we do is the training task is, and this is what OpenAI have hired a lot of contractors to do, is to generate examples of a question and the perfect answer to that question. And then those question answer pairs are given to the large language model to continue training so that the format of the answer is now in a Q&A format. So that's really good, because now we don't get like random completions. We get an answer that looks like an answer. Importantly, you can't really, not all questions have a perfect answer. So this instruction tuning phase is restricted to questions that are univalent, that only have really one great answer. Next phase, the next step is preference optimization. And in preference optimization, the task that we're going to do is we're going to take polyvalent questions. So for example, if I ask you to write a letter to Santa Claus to ask or to tell him how much you like him and what you like for Christmas, there isn't really the best answer. There isn't really one answer to that question. There may be many good answers to that question. However, as humans, we might have a preference for one type of letter to Santa Claus over another one. Maybe a kinder letter is a letter that we would prefer over a letter that isn't so kind. So in preference optimization, we don't say, here's the question and the perfect answer. We say, here's a question, and we have two answers, and we prefer this answer a little bit more than that answer. So we're saying we're optimizing our preference in the output that we're wanting from the large language model. And so that's another really big step in quality of the output of large language models, because now not only do we get answers that have the right format, but also we get decent answers to polyvalent questions like write me a poem about X or write an email to Y. So this is really where we are now, and this is already kind of really amazing. However, that's not the end of the story. There are still things we want, right? We already talked about the reasoning and planning abilities not being at the level that we want them to be at yet. And the question is, what do we need to do to improve the depth of the T, to improve its reasoning and planning abilities? I don't think we know yet, and I think there are companies working on this, but it's not yet known what needs to happen. Maybe we even need to change the architecture. Maybe it's another training step. Maybe it's the result of training on even more data. All right, so I hope that kind of shows that while the result is magical, the internals of it are not necessarily magical. Next up, I want to show you a few of the types of applications you can build, the types of experiences you can build with large language models, and a mental framework that you can use to design your own applications. So returning back to the T-shape, what is the goal of an LLM app, an LLM application? It is we want to provide a better experience for a more narrowly defined task. A large language model or ChatGPT is good at many things, but it's a master of none. And in this case, with an LLM app, we want to improve the quality by narrowing down the domain, by saying we want to solve a more particular type of task, and we want to do it better. So increasing the depth. So we want to get rid of hallucination. We want to kind of guide the reasoning. As humans, we have an intuition behind how an LLM can be, how its reasoning can be broken down into steps that will arrive at the desired results. And we can also guide it in terms of its planning abilities. This is the anatomy of an LLM application. So the first thing that I think is important to know about this slide is that you should no longer think about large language models as a chatbot. a large language model is not a chatbot. If there's like any takeaway from this presentation, it should probably be that. A large language model, a better analogy for a large language model is that it's like a cognitive CPU. It's like an engine that you can use to connect different modules with each other. So, for example, we've looked at one, the portfolio assistant that I demoed in the middle of the presentation. That is an example where we use a large language model to generate code. We feed the code to a module, which is in this case Python, the Python programming language, the Python interpreter actually. The module executes the code. The result is sent back to the CPU, and the cognitive CPU says, okay, there was an error, I have to update the code, send it back, or it says, the result is what I expected. This is something I can send down to the user. So an LLM app, you should think of the cognitive CPU as something that is an enabler in that it connects different modules and makes different experiences possible. So I'll give you a few more examples. Oh yeah, so given that this is the structure of an LLM application, how do we improve the depth, right? I didn't really answer that question. So this graph that you see here, the y-axis is let's say a measure of intelligence of the large language model or of the application. And OpenAI have taken several steps, and other large language model companies have taken several steps to improve the intelligence of the instruction of the base large language model, but also of the instruction tuned version of that large language model. But to continue improving the intelligence, to improve the quality of an LLM app, there might be several additional steps you may want to take. Those steps, when you take them, they narrow down the domain, but in return for narrowing down the domain, you do get an improved quality of the results. It will probably lead us too far to dive into these different techniques, but there are several techniques you can use to do that, ranging from zero-shot prompting all the way to retrieval, which is one of the bigger ones, and up to parameter-efficient fine-tuning. Each of these techniques, if you apply them, let's say they can reduce the amount of errors by approximately half. So here's another example where we're using the large language model as a cognitive CPU. The idea is we want to generate a personalized podcast. So one way you could do that is you could say, okay, I'm going to use a network module to fetch all of a user's articles so let's say a user is subscribed to several news websites, and those news websites, they have maybe an API to retrieve recommended articles for that user. So using a network module, you can, or the LLM can even decide to call that network module, you can fetch the recommended news articles for a given person. The cognitive CPU can say, okay, I'm going to read all of these articles, and I'm going to condense this down as a first step, condense this down into the kind of the key highlights, the key messages I would like to bring to the user. Next step is the cognitive CPU can say, now I'm going to take those key messages and transform that into a podcast script. A podcast script maybe with a host and a guest. And that podcast script can then be handed over to another module, for example, an audio or a speech module that takes the individual sentences by the podcast host and guest and transforms that into speech, ultimately producing a personalized podcast that the user could listen to on let's say, their morning commute, condensing down all of the most interesting bits of information in an interesting podcast, which you can then publish to, for example, Spotify or Apple Podcasts. So that's another really interesting type of application, really very different from the previous one, where we're using different modules and using the LLM as an enabler for this application. I do have a demo of this because with InvestSuite, we actually developed a prototype that does this for a product called Storyteller, which tells you the story of your investment portfolio's performance. But I'm going to skip it in the interest of time. Yeah, you can imagine other experiences. For example, here's a book experience where we have a module that has maybe files, maybe the chapters of a book as different PDF files. And actually, there was a book that was recently published by Tyler Cowen, very recently, I believe, which he calls a generative book. What he did was he created a custom GPT where he uploaded all of the chapters of his book, and basically it allows you to talk with his book, basically ask it questions, and you get answers because of the way that he prompted. I'm assuming you get answers that would be how he might have answered that question based on the contents of the book and based on his knowledge, which is a really interesting new way to explore the contents of a book. So those are some examples of different types of applications. Let's say the CPU approach is maybe a mental model you might be able to use for your own applications. What does the future hold? I'll try and speed up because I'm a bit mindful of the time. So I think there will be 3 steps. The first step is we'll all start developing these individual LLM applications that make different experiences possible, improve efficiency of certain processes. We looked at a few, like the portfolio assistant, the personalized podcast. Maybe you can generate an LLM app to help you answer your emails if you're working at a help desk, for example. That's one that Radix gets quite often as a request. The book assistant, and so on. So over time, we'll develop these LLM applications. And from there, the thing is, you'll have this multitude of LLM applications, so we need a way to interact with them in a better way. Maybe we'll see this shift from everyone has a personal computer to everyone gets a personal intelligence, which is kind of like this gateway to all of these LLM applications. And that gateway could be what many companies are calling copilots. So for example, Microsoft has their own copilots, Google has Bards, OpenAI has ChatGPT. And for example, ChatGPT, you might not realize it, but they also have this kind of a store of different, what they call plugins. Now they're called GPTs. And so from this one application, you can kind of interact with all of these different underlying LLM applications. And so the same is probably going to happen with the Microsoft suites and with other kind of ecosystems. And the principle is that we have a user. The user initiates a conversation with a question. The copilot interacts with one of many LLM applications and comes back to the user with an answer or an action suggestion. That's definitely one trend that we're witnessing now. From there might be a third step, which is that notice that here the user asks the copilot a question, the copilot comes back with an answer or an action suggestion. In the next step, maybe it'll be the reverse. Maybe we'll have digital colleagues that actually reach out to you and say, hey, I have a question for you. I'm missing some information, or I need you to validate this decision or action. And that we don't have LLM applications, but that we have digital colleagues that are working besides humans, also interacting with the LLM applications, but working beside humans and reaching out to humans when necessary. And we're starting to see that becoming a reality slowly. Here's a recent article from Forbes discussing this very idea. I'm going to skip this because I'm really running out of time. Skip that as well. Or maybe I'll end with this. So I talked about AGI. Not many companies have the resources necessary to be able to develop large language models and to potentially working on developing AGI. There are some companies that have those resources here. This isn't an exhaustive list, but these are certainly companies that have, let's say, 10,000 H100 NVIDIA GPUs or more. H100 being the latest generation of GPUs, which are used to train large language models. And I've attempted to write down what I think their focus might be. This slide is a little bit out of date now, but this could be their focus in the development of their large language models. And you can kind of see that many of them are focusing on this reasoning and planning, increasing the depth of the T. So that's really where I think we're headed, is to increase the capabilities of large language models, to increase their depth. There are some predictions about AGI. Here are some more well-known people in the field that have made statements about AGI. Sam Altman, the CEO of OpenAI, has said recently in an interview that he thinks that we're less than 10 years away. although he's updated that. I think he made a more recent comment somewhere where he says that it's probably even less than that. Mustafa Suleyman was a co-founder of DeepMind, now Inflection AI. He says we might achieve AGI level within 18 months. And Shane Legg is the, I believe, chief AGI scientist at Google DeepMind. He says he made a prediction, which he's still standing by, which is that it could be as early as 2025, but maybe more like 2028. And on a final note, there are those who believe that we'll get there simply by scaling up. That means training on more data, and that the properties that we desire will simply emerge. So the reasoning abilities, that if we throw more compute and more data at it, that will get better or reasoning and planning capabilities that are of the level we want. However, there's this scaling law called Chinchilla's large language model scaling law, that kind of predicts how good, and it predicts it to quite a high degree of accuracy. It predicts upfront, even before you've trained any model, it'll tell you how good your model will be. It's kind of like an empirical law, which turns out to be quite accurate. And this law tells us that if we exhaust all human training data, we still wouldn't really make a lot of progress in terms of the quality of the large language model. So we might be bottlenecked by the amount of training data, the amount of text that is available to train large language models on. But that is to be seen. Who knows, maybe we can teach large language models to learn from their own output, which is what we do as well. So yeah, that's it. That's the end of the presentation. Thank you. Any questions? Yeah.
Thank you. So we can follow you.
It's like this. Oh, this. Okay. Yeah. So one question I have is this. So the large language model try to predict the next word.
Yeah.
So when the output, like in the application, for instance, like Google emails, we see that it gives you prediction. So
yeah.
At the back end, it's some LLM model working, and at the output, the user only see the one word. But does the model after the software function, does it give you all possible words in entirety in the world with their likelihood, or is just some limited 5 or 6 words with their probabilities? I mean, at the back end, what is happening?
Yeah.
Like trillions of words with each probability, or just 10 most likely words with their probabilities?
No, for each next word, it actually will generate the probabilities for every potential next word to complete that, or to follow up on that sentence. And then it'll pick one of them, weighted according to its probability.
Mm-hmm.
So it doesn't necessarily pick the one with the highest probability, but it picks one of them according to the probability. And you could, in theory, there is nothing stopping you from writing down the probabilities so that later on, if you want to inspect the probabilities of the words, you can actually look at them. That is possible. It's not possible in like Gmail, because there they only show you the actual text and they don't show you the probabilities. But behind the scenes, I'm quite sure you would be able to look at the probabilities and look at alternative completions as well. It's quite easy to generate alternative completions. You can do it as well. Just ask the same question multiple times and you get a completely different answer. Well, maybe not completely, but certainly a different answer each time.
Yeah. And I have one more question, but it's not related to LLM, but rather like for me, like I'm a bit of an enthusiast about AI. I come from a different background. Like I have an engineering background, but not in computer science. And then I've worked mostly with banks in the IT sector. But now I have started to learn, the machine learning. Basically, I'm doing some courses, following something, and planning to gain more and more knowledge. And probably, if really possible, then maybe a full-time degree. But then people like me who have already have work experience of more than 10 years and now trying to switch, is it a good approach just to go take a degree? Or I mean, you can learn, but then how do you make a career switch is something which is not super clear to me. I know it may not be a right platform to ask this kind of question, but some kind of guidance might help, give you some idea.
So I definitely think it's a great idea to get to know the technology, to learn how to use it more effectively. That, like, as a user, like being a user of this technology is probably one of the most effective things you can do to help yourself and navigate through what's coming. Do you also need to learn like the underlying, machine learning and technology to build your own models? I think that's valuable mostly if you want to develop your own LLM applications, which I talked about. If you want to develop LLM applications, I think it's very useful to have a bit more of the background knowledge about what goes into building large language models, machine learning models in general. If you see yourself more as somebody who wants to leverage the AI to make yourself more productive, I don't think that's really necessary. It depends on what you want to do, I think.
Mm-hmm. Okay, thank you.
There we go.
Thank you. Given that there's a limit to the performance achievements that we can achieve by scaling up the data we input into the LLMs, and the competition that OpenAI, for example, is facing from open source models, do you believe that the LLMs themselves, the base model, will become commoditized? And if so, where will the real value actually be generated?
So I think there are multiple questions in there. Do I think they will become commoditized? I think it's likely that we'll have a lot of large language models generally available for everybody to use, even in a permissive way, so even in a commercial context. For example, Meta has released several large language models that are quite good, actually, the Llama series of models, to the public domain, more or less. And I believe Mark Zuckerberg has also recently said that he wants to open source the newer developments that they're still working on as well. So that makes me hopeful that we'll have that large language models and the successors thereof will be widely available for anybody to use. As a commodity, yes, then I would say as a commodity. Where will the value lie? So if you look back at the recipe for success, here. So what I didn't explain is that the pre-training phase, that's the one that costs hundreds of thousands, millions of dollars to actually run. So this can only really be done by a few companies, the ones that I put on the slide at the end. But once this is done, and if this is shared publicly, all of this anybody could really do. So yeah, and a lot of the value, I think, is kind of in a way in what happens here, because of the reasons that I shared afterwards. You want the format to be right, you want the quality of the answers to be right, you want the reasoning and planning skills to be there. It's difficult to predict with certainty, but yeah, I think if the base large language models are generally available, I think a lot of people can create the value themselves that they need. And we're seeing that in open source already.
Can you share some of the actual applications by corporates in their usage of LLMs?
Some applications of corporates, yeah, maybe a common one is making help desks more efficient. So there's like a common inbox with a lot of questions maybe, and they want to be able to process those questions more efficiently by drafting answers to the questions with large language models based on previous inquiries, based on documentation that they have. That's certainly a big one. Another one is maybe interacting with databases, like a SQL database, so a lot of companies, they have business intelligence teams, and they get questions from all over the place. And so they need to translate those questions into usually SQL queries that result in some kind of reports. But if you can go directly from the question that the business has to the SQL query and then execute it and produce the graphs, kind of like I showed in the demo, that makes the BI team way more efficient. Another example could be creating documents. There may be many types of documents. Maybe you need to respond to an RFP. Maybe you need to write legal documentation for regulatory purposes. So helping to write documents is another one. Those are a few examples. Yeah.
I've seen a help desk implementation and it blew me away. It's a bit why I'm here. I'll just, in 10 seconds, I'll explain to people. So EDI, Ditterin, if you charge your car, it's EDI. And they implemented, their help desk was a nightmare. And I happened to be, I was working in Ditterin and I also have an EDI born and I was having problems. It went on for a year. And a few months ago, they put in an AI thing. It reads the chain of, ping pong would have read all that. It summarizes all the emails. It ranks what is the level of frustration. So for me, when I got a colleague who did it to pull it up, it said I was frustrated. The summary of my problem was amazing. And then it summarized exactly what the problem was. And on top of that, it gave 10 checklists for the help desk person. And it costs about €1 a day to process the whole chain. But once they implemented that, they went from a situation where EDI had maybe the worst help desk in Belgium. It's terrible. Everything's just, nobody's getting answered something. Within a few months, they're going through them. It just blew me away how good it was.
Thank you for the presentation. I have many questions. One of them is, what happens if language evolves, if we get new words or new meaning to existing words, new grammar structure? Do you have to train or retrain it all?
Yeah, currently, that's a good question. Currently, large language models are, I want to say immutable, so that's maybe not the right word, maybe static. That means that when you interact with ChatGPT or a large language model, it doesn't actually change. It's the same large language model whether you interact with it today or tomorrow, or whether you've been interacting with it for a month. The only time that it changes is indeed when they do the pre-training or the fine-tuning steps. So if there are actually new words, then they would need to update the model with additional training data, either in the pre-training stage or in the fine-tuning stage. Currently, but maybe over time we'll learn how to make the models learn from each individual interaction, and maybe then that's no longer necessary.
Yes, hi, thank you for the presentation. I'm curious to understand a little bit what it looks like to actually work in an AI company or to work around AI. So you mentioned in the training stage that they hired a bunch of people to actually redact examples of questions and answers and what we want them to look like. Mm-hmm. You've also talked about task accuracy, so I'm curious how that is measured. And of course, I understand there's a consulting and advising, but I'm really more curious to the actually working with it in the training or the evaluating of the AI. And do you mean companies like OpenAI that are developing large language models, or do you mean companies like Radix who are building large language model applications? Both. Well, the OpenAI, I guess it's more complex, but maybe more about the applications. Okay. Okay, I'll try and give you a sense. So in a way, the first step is to really understand the problem, to really understand what the client is trying to achieve, making sure that you fully grasp what their goals are, what they really care about. Once you have that, you can translate that into some kind of measurable way to measure the success of the project. And then with that in mind, what we do is we develop a solution architecture, which is like it's really just a diagram with some components that link up to each other that ultimately solve the task or the problem that the client has. What goes into such a diagram? Different types of components. Usually a key one is called an LLM orchestration tool. There are many different software packages because as we saw, large language models are really very basic at their core. What they do is they predict the next word. And so you can get it to predict the next word, or you can get it to predict a series of next words, let's say. That's really the core of what a large language model does, but that's clearly, that's way too basic to
have or to use as an application itself. An actual application would need way more logic, way more steps to go from the inputs all the way to the outputs. So the question is, how do you program that whole flow? And that's done using LLM orchestration tools. Some examples are Llama Index for RAG-based applications, LangChain, Prompt Flow, Semantic Kernel is another one. Those are all software libraries that you can use to interact with large language models to build an application, to build a broader thing, and to implement some of the performance improvements that I briefly showed in the slide deck. And then so then maybe you've implemented that diagram that you've created, and then comes a really important phase where you need to evaluate the LLM application. And that is, I don't think that's a solved problem. It's quite difficult to automatically grade the quality of the output of an LLM application. How do you do that? You can ask humans clearly. You can say, okay, you sit a human at a computer, you give them the LLM application, you ask them to produce some inputs, check the outputs. Is that what you want? For example, in the help desk case, is the response to the email a good response? In the podcast case, is this a podcast I would want to listen to? You know, different applications require different ways to measure that. But one technique there is to use a large language model to grade the quality of your LLM application. The reason for doing that is it's simply not scalable to ask humans to interact with your application every time you make a change, to go ahead and say, okay, we've updated the application, can you try it out again and tell me what you think? That's not really scalable. It requires way too much time. So instead, what we do is we say, we actually ask another large language model to say, hey, here's an example interaction produced by this LLM application. What do you think about the outputs? Of course, you need to do that in an intelligent way as well. You need to think about how you want the evaluating large language model to grade the outputs. But if you do that well, you can make the evaluation phase way more scalable. And there are even ways to, if you build an LLM application, there are even tools that allow you to kind of optimize the whole flow end to end in a similar way as an LLM is trained, actually. So that's another thing, but that's still quite new, I would say.
So we have been able to train AI to train AI in a way?
Yeah, that happens quite a lot.
Okay, and to evaluate as well.
Yeah, to evaluate, to train. There are often multiple levels of optimization.
Okay, thank you.
Yeah.
So when it comes to build LLM application, so there are certain industries which are very restrictive about their data. So like most, I have interacted with ChatGPT, but it's like you have to send a query, which goes to OpenAI's server, get processed, and you get an output. But there are industries which are very sensitive about their data, and they do not want to push anything to OpenAI or any other's server.
Yeah.
So is it possible to have these model in their own in that particular industry's servers, or you always have to go to that particular OpenAI server?
No. So there are that's a very valid concern that many companies have, and there are several solutions to that problem. For example, OpenAI's API. So GPT-4 is still, I would say, the best large language model currently available. So a lot of companies want to work with that one because it simply provides the best quality outputs. But they're indeed hesitant to share data with, especially larger companies, to share data at scale with a company like OpenAI in the US. So some solutions could be, for example, Microsoft offers the exact same OpenAI large language models, but hosted on your own Azure subscription. So that's a way to make it private, and Microsoft provides additional guarantees, I believe, on that there won't be any logging, that the data that is sent to that API is not actually sent anywhere else. So that's one way to deal with it. Another way is to use open source large language models, which you can either have hosted for you with other service providers, or like, for example, Together AI is an example of that one. Or you can choose to host your large language model, an open source large language model yourself on your own infrastructure. That would be another solution. This could be on premises or in your own cloud. So many strategies to deal with that.
All right. One last.
Thanks. Just a small question. Because you show Mistral on one slide, they came like a few months ago.
Yeah.
I was just wondering, because maybe you use it, if it's really better than ChatGPT 3.5, maybe not the 4. And did you use it? What's your experience with Mistral?
Yes, we've definitely used it. I would say we're big fans of Mistral and the LLMs that they're releasing. I love the fact that they've put it out there as open source. In terms of quality, we don't actually use GPT 3.5 all that much, maybe during developments to kind of cut down on the costs. So it's difficult to compare with GPT 3.5 directly. But just from interacting with Mistral's models, especially their latest Mistral model, the quality is really very good. It's kind of amazing to see what they're able to achieve with such a small team and the resources that they have. One way to kind of gauge the quality is to look at, there are 2 leaderboards that compare basically most large language models. And they're actually ranked really highly on both. I think, if I'm not mistaken, the Mistral model, the latest one, is the highest ranked open source large language model available today.